Okay, so today is our 7th lecture. We are continuing to study interval exchange transformations, moduli spaces, and some related stuff. And today we have a very ambitious project because I'm supposed to prove, at least I will try to complete the proof of Mazur-Veach theorem. I recall you that we stopped previous time on two different aspects. We want to prove that almost all interval exchange transformations are uniquely ergodic, and we also want to prove a statement about the finite measure for some pieces of moduli spaces. Last time I left one statement without proof. Probably I should say a few words about it. So I just recall you, it's a technical statement, so I'm not going to do it in details now, but it was a statement proved by Marmi, Mossai, and Diakos that if we had a finite path that was a concatenation of a sufficient number of complete paths on the diagram, then it was enough to say that we have all the coefficients of our Rose induction matrix strictly positive. So it's a finite path. In a Rosy diagram that can be written the concatenation of 2D minus 3 complete path D here is the number of letters in our alphabet, so it's a number of subintervals for our interval exchange. So all coefficients of the matrix B gamma. B is the matrix of the Rose induction, and it's the way how do we express all coordinates in terms of nu1. They are strictly positive. So the proof is quite technical, and since we are a bit in a lack of time, I'm not going to reproduce it now. It can be found on a paper by Marmi, Mossai, and Diakos on cohomological equations for interval exchange transformations. It will be an important point, and I recall you also the very end of the previous lecture where we discussed briefly the idea how we want to apply it to prove unique ergodicity. Namely, we introduced the following objects. We considered our open cone, B gamma n B gamma 1, so it's a convex open cone. And we consider the intersection. If we have an infinite path, then we will need to consider the pieces that are attributed to each finite part, and then we have to intersect them all. So this is a set of length data that corresponds to gamma. And we used it to prove the estimation on the possible number of invariant measures. And I'm going to use it today again. It will be my main ingredient for the proof of a Mazur-Veach theorem. So as I told you, the general idea follows from the fact that we will use this strictly positive estimation. I will introduce a special metric, which is a Hilbert metric in a projective space. And then, since all the coefficients are strictly positive, the corresponding projective map will be strictly expanding or strictly contracting, depends on the direction in which you follow your induction. And so you can use the logic similar to what we use when we prove the nested interval statement in the calculus of the first year, right? So we will get every time a smaller and smaller piece of the parameter space that will be associated with the length. And finally, we will be able to show that we have always array, almost always array. But this will require some additional work, and this work will be quite demanding. I will explain why, but in the meanwhile, so let me apply it to get some information on possible number of the invariant measure. So we have interval exchange transformation. I recall you that we have combinatorial data, top and bottom. Assume that our interval exchange transformation is generic in a Keen sense, so we don't have any connections. And thus, in this case, I should be able to apply Rosy induction as long as I want. And so I have an infinite path on the Rosy diagram. This path is associated with our interval exchange transformation. And as we wrote there, we have C of gamma, which is the intersection of this Cn. And then I will introduce M of t. It's the set of finite measures that are invariant under the action of our interval exchange transformation. And Ci of gamma, we claim that it's in one-to-one correspondence with M of t. So the information about the dimension of C of gamma is indeed the telling in a sense of the dimension of the information about the number of invariant measures. So let's try to check that it's true. First, we take lambda that lives in C of gamma. So lambda means that we take a vector of length such that the corresponding interval exchange transformation will have gamma as an associated Rosy induction path, right? So we choose length in a way that if we take this permutation, then we will live the prescribed life in the Rosy diagram. And now we associate T of lambda with this set of length. And then we take U of lambda. It's the largest. So U and U of lambda, it's two different points. It's always the largest singularity of t minus 1. This is our original interval exchange transformation. And this one is the one that we constructed using this lambda. So and now we will consider the orbits of this U and U lambda. So we take the orbit under the action of T, and we take the orbit under the action of T lambda. There are two orbits. Both of them are dense, right? Because we agreed that we have no connection, so we satisfy Keen's condition, and thus all orbits are everywhere dense. So these two guys both have to be dense. Now, if they are dense, what can we say about it? We can consider the map that takes us H. It will be from Tn lambda U lambda to Tnu. So for each n, you make one-to-one correspondence between these two orbits. But note what happens. We took lambda that lives here. Here is the intersection of all this Cn. So you already applied all these matrices. And thus it means that you have a shorter interval, shorter support interval. So if we have such a map here, then I claim that this map is always increasing. Because this is what corresponds to these points, to the big interval, and this is what we have at a smaller interval, the shorter interval. So this should be increasing. because they both have the same path at the Rosevich induction. And so then I claim that I can extend H to the homeomorphism from the whole E lambda to E. Because we had this map, we constructed it manually, then it was everywhere dense, and it was everywhere dense, so we could automatically extend it to the homeomorphism of the whole interval. And moreover, we would have that the composition of these two people would coincide with the composition of these two taken in the opposite order. So they are conjugated. That means that T lambda and T are topologically conjugated. So now if we consider the opposite map, so we will consider the H star, and we take the reduced map, and we take the Lebesgue measure on E lambda. What it will give us, it will be projected by this conjugation to the measure on E, on the original interval. And this measure will be of a total mass that corresponds to the length of the interval I lambda. So, and this measure should be invariant under T because of this conjugation. Thus, to each point that lives inside of this cone, we constructed a corresponding measure. So now we need to check the opposite, that if we are given a measure, then there is a point here that corresponds to this measure, and then we will have one-to-one correspondence, right? So let's do it. So conversely, if we have a finite measure, this measure is invariant under our interval exchange transformation T. And we take some alpha. So the length will be given. This T and B, they correspond to top and bottom. So the lengths, they are Lebesgue measures of these intervals. And then we can also define the following map that will be defined on the whole support interval. And so this map is just the set of y. Y is less than x. So we know that T is minimal because we agreed that we will always live inside of the Keen's set. Thus, this minimality of T in particular implies that mu is quite nice measure. Mu has no atoms. The support of mu is in E. What does it give us, this fact? In particular, it gives us that K, that we define here, should be an homeomorphism. K is homeomorphism. And how does it act? it takes I, our support interval, and it's a omeo onto 0 mu of I. I will denote it E mu. So I can associate T mu with it. And T mu is a result of the conjugation of my T with K. K is a conjugative map. Why it's homeomorphism? Because your mu is a nice measure. So what does it mean to be a nice measure? It means in particular that it has no atoms. And so what you take a Borel set and you measure this Borel set. Your mu allows to do so. So then you consider the pre-images, and you see that they should satisfy the conditions, right? So it's a very standard measure theorem. So you can conjugate interval exchange with this K, and you get T mu. And what can you say about this T mu? It should preserve the Lebesgue measure. And additionally, it's easy to see that it's also an interval exchange transformation. And since it's an interval exchange transformation, it should have some combinatorial data, and it should have some length data. So then I associate it with each measure an interval exchange transformation, and vice versa. With each interval exchange transformation, I could associate a measure. So there is one-to-one correspondence, as I promised you. So this will allow me to estimate the number of invariant ergodic probability measure. And that's what I'm going to do right now. So we are given an interval exchange transformation. This is its support interval. And G will be the genus of the translational surface that I built starting from T when I apply zip rectangle construction. So it's a genus of the translation surface. And as we agreed, we have the correspondence between M of T, the number of measures, and the cons that we construct in this way. So I'm going to prove the following proposition, that the con in which I will add 0 is a closed simplicial cone whose dimension cannot increase is G, where G is the genus of the corresponding surface. And I claim that it implies that the number of ergodic measures we add the normalization, so I would say ergodic probability measure is less or equal than G. We will discuss it in a second. So what I mean simply is that you have it as a simplex. I mean that you have some list of vectors and you construct it as a combination of these vectors. So it's like a tetrahedron, but you increase the dimension. So you have ages, morally. That's what I mean by the word simpletion. That you have this cone, and you have ages for this cone, ребра. And why it's important? Because there is a Bogolyubov-Krylov theory that tells you that if you have a set of all invariant measures, ergodic measures, they are exactly this kind of basis that you can use to construct all the invariant measures. So this will be a role of ergodic measures, and since if we are able to prove that the dimension is estimated like that, then it's almost automatical that the number of ergodic probability measures is also bounded by the same number. Okay, so let me continue. We're going to prove this proposition. So the fact that it's closed is rather obvious. I need to explain why it is simplicial, and the reason is actually because it can be identified with a set of measures. Because for the set of measures, we know that it has extremal arrays from Krylov-Bogolyubov theorem. So we know that then these extremal arrays for C of gamma, they correspond to ergodic invariant probability measure. And these measures, they can be written in a unique way as a convex combination of ergodic ones. So what remains to be checked is the statement how it can be related to the genus of the surface. And this is what we need to do. So I recall you how this genus of the surface can be interpreted. You remember we had the set of lengths, and we had pi as a permutation, and we used pi to construct some famous antisymmetric matrix. Maybe you remember we had to put 1 or -1, depending either we have a shift to the left or to the right of the corresponding interval. So this is our antisymmetric matrix. And this matrix was also the intersection form in homologies. It had a very precise topological sense. So we knew about its rank, and we will use it. So my first claim is that if we take the E as a subspace of the set of lengths that is generated by my C of gamma, so this E intersected with ker sigma, it's 0. This is my first claim. I will prove it, but before I do this, I will tell you the general logic of the rest of the proof. So I will check that the image of in the factor of care. So these are vectors that are annulated by our application of our antisymmetric matrix. So this is isotropic for the symplectic form determined by our antisymmetric matrix. And then this second point will exactly imply that since the rank of my omega is equal to 2G, then its isotropic subspace absolutely cannot have the rank that would exceed G. So that will be the main instrument how I'm going to prove my estimation. And the reason why we have G here is in reality because the rank of this antisymmetric matrix is equal to 2G. Okay, so now we have to check that these two claims hold, and this I will do in a second. So we prove claim number 1. We take two vectors who live in C of gamma, and V minus V prime should live in the care of our sigma. Sorry, of our omega. So we have to check that this intersection is 0. So we assume that it's not the case, and then we do this. So now we take the initial part of the path on the Rossi diagram. So it's initial part of gamma. Since they both live in this apartment, they share it. So then what does it mean? That if we take V minus V prime multiplied by B minus 1 gamma of n, it should depend only at the end point of gamma n. It follows from the properties that we proved when we studied symplectic properties of our induction previous time. So now if we consider these things, they go to 0, because that's what Rossi induction does. And that's what we have. We have two sequences. They both go to 0, and they are identified by the end part of the end point of gamma n. So we can conclude that they should be all zeros. Otherwise, it's impossible. We would have different values here. And it will contradict this statement. So simply, V is nothing else as V prime. Okay. Now we have the claim number 2 that we also want to check. Assumes that it's not true what is written there. So they should be two vectors, V and V prime. Once again, they both live in C of gamma, such that V omega V prime would be strictly positive, right? Unless this is true. So unless this is isotropic, if it's not true, then this one should be true. we should be able to multiply our antisymmetric form, one on V and one on V prime transposed, and we have supposed to get a positive vector. But once again, we have this property because we live here, and we have this property because we live here. So what we have then, we can write it as V, B, gamma minus 1. Then you take omega n, and then you take B gamma minus 1 transposed, V prime transposed. So then you here you have simply the same, and so you have V omega t V prime. Sorry, no, it's just omega itself, and t is here. So then you concluded with the statement I wrote here that the rank of this omega is exactly 2G, so isotropic space cannot have the dimensions that would exceed G. And apparently this bound was established first by Katok. It's his result, even if the proof we reproduced here is by Vich. And then Katok's student, Sataev, proved that it's optimal. He constructed examples of interexchange transformations when you have exactly G invariant measures, ergodic invariant measures. And his result was later rediscovered in some aspects by John Fickenshire, who was a student of Vich, and it was his PhD thesis. It was not really rediscovered because Sataev spoke very, very different language. He was considering some flaws on surfaces, while Fickenshire really works with interexchange transformations as they are. So they both proved that there exist some examples with G measures. And I gave you in the Google Classroom a list of possible topics for the presentation, the oral presentation. And one of the possible topics is exactly to explain the logic of how to construct non-uniquely ergodic interexchange transformations. As you already heard, we have not proved it yet, we will do it today, but you heard already that a typical interexchange transformation is uniquely ergodic. So we are looking for some exceptions. And then I propose you to take one of these examples to learn, to discuss it later, how this example should look like. So that's what these people did. And in reality, you can construct whatever number of measures between 1 and G, where G is the genus of the corresponding translation surface. So now what we are going to do, we want to prove this statement about unique ergodicity, but we also want to be able to prove that the Dirac-Müller flow that I defined on one of the previous lectures is ergodic. And so our approach will be the following. You remember that when we were studying the geodesic flow at the surfaces, we finished this study with a theorem that told us that the first return map for the geodesic flow on a modular surface is nothing else but a fraction algorithm. So here we will try to reproduce the same logic, but as a first return map, we will have not the Euclid fractions, but the Rosevich induction. And so we will replace the study of ergodic properties of the Dirac-Müller flow by the study of ergodic properties of the corresponding Rosevich induction. So that's our plan, how we would like to arrive to this statement. And you will need to be quite patient following me in this journey, because it will take a lot of efforts. But these efforts, they are very meaningful, because in the meanwhile, we will also be able to learn a lot about the geometry of the corresponding modular spaces. So since our goal is to study the Rosevich induction as a first return map, we need to understand it slightly better. And in particular, we will see that it's not convenient to work with the Rose induction as it is. I will give you now some kind of vulgar explanation why it is the case, and I will explain you what we plan to do, and then I will do it much more formally, and you will need to be patient watching it. So the idea is the following. Let me recall you how did we define the Rosy induction. So we had interval exchange, and imagine that sometimes we could have a very long one interval and very short others. And then what will happen when we apply the Rose induction? We will always have the same winner for a very, very long time. And then the corresponding matrices will look like that. So you will have like 1, 1, 1, 0, 1, 0, 0, 0, 1. And you will continue to iterate for a while up to the moment when finally you will change the winner. As we discussed on our previous lecture, all of them, if we want to have infinite paths at the Rosy diagram, and that's what we are supposed to have if we have Keen's interval exchange transformation, so at some point they will need to change their roles, and even the winner will become shorter than other guys. But it may take infinite time sometimes, because one can be very long. Infinite, not literally, but it's the time for given lengths, it's always bounded. But if you consider the class of all interval exchange transformations, it can be very long wait. And during all this time, you always have one column that does not change. So this may increase, and this guy will be always preserved. And so you get a very unbalanced vector. And then, if you try to understand what's going on, you will multiply, compute the Jacobian of the corresponding projective map. The projective map comes from the fact that when you apply the Rose induction, you get a shorter interval, and then you can renormalize it to get back the interval equal to 1. You understand? So we do this. When you apply the Rose induction, you cut this interval. And you lose this part. This. So the interval becomes shorter and shorter, and if you want still to preserve the condition that allows you to keep everything in a simplex of a finite dimension, when you add this normalization condition that the sum of length is equal to 1, after you apply the Rose induction, you will need to renormalize to extend it again to the whole interval. So if you do that, you get a projective map, and you can compute the Jacobian. And this Jacobian will have a fixed point. In the point that is like 1, 0, 0, 0, one interval is very, very long, and the others are close to 0. If you have the interval exchange like that, then basically it takes you forever to leave this fixed point. So it's bad for the analysis of the corresponding dynamics, for the analysis of the ergodic properties of corresponding Markov shift. So our idea would be to accelerate the Rose induction, to accelerate our algorithm in a way that we will have a finite number of steps of this accelerated algorithm every time. So what do you do when you divide numbers? Imagine that you have a very big number, and you have to divide it on a very small one. So kind of the first step that people usually do, like my son in the first grade of primary school, he would subtract this number many times. And then it's a very crucial psychological change that at the second year they already do not subtract, but they divide. So they immediately consider as one step of their new algorithm all the corresponding steps when they would subtract the same number, right? So here we would do the same thing. What I'm going to tell you now morally corresponds to the idea that instead of making one step after another, I can consider all the steps where the winner was the same, consequently, as one big step. And I can analyze an ergodic properties of this new algorithm, so, because this new algorithm will not keep fixed points in this annoying manner that we just discussed. So that's the reason why do we care about it. And if you prefer to think about it in terms of the geometry of the modular spaces, you may think that the problem is that when you define a measure that lives in this modular space, there will be some points where the measure can be infinite, because you can spend infinite amount of time around this point. It's this fixed point. So you want to get rid from this problem. And so you will consider the measures with respect to these new accelerated algorithms, and these measures then will be finite. That's the bright idea that Anton Zoric had. And so that's what we are going to discuss now. But in order to make it explicit for us, we will need to think a little bit more what's going on inside of the modular spaces. So this was kind of heuristics, and now we are going to the formal part of the Rosevich dynamics. So we consider our simplex. For a moment, we do not renormalize. We keep it like that. And then we fix the diagram. And so we will have the Rosy diagram and the corresponding projective space. So now we add renormalization. And then the Rosevich algorithm induces the map from delta to delta. That's what we discussed now when we were talking about the need to renormalize. And so for each arrow at our Rosy diagram, we will have a winner and a loser. And we can consider half of our parameter space that would correspond exactly to this choice of the winner and loser. And the domain of V plus is the union over all the arrows of the composition of people like that. So each simplex in our delta D, identified by the vertex, it contains two components of the domain of V plus. So each is sent to the full measure of delta plus. So what I want to say is the following, that we started with the parameter space, and I do it as a two-dimensional thing, but you should imagine that you have much more complicated guy who has many dimensions, because the dimension is identified by the number of intervals. And now I have to divide it into two parts, depending who was the winner and who was the loser. So I have a kind of partition of my set into two parts. One would correspond to the choice when alpha 0 was a winner, and one would, the second half is when the other guy is a winner. And then what my renormalized Rosevich induction allows me to do, I can construct a map from this half to the whole parameter space. This projective map gives me that. And so I have, from each half, I have a map to the whole parameter space. So each is sent, each half, is sent to a full simplex delta D. And so my V plus is 2 to 1. And I will consider S of D. It's an important guy. It's just a union over all vertices of my Rosy diagram of the permutation P delta and P theta pi, where theta pi is the guy who gives me suspension. Because you remember, we deal with not with Rose induction, but the Rose-Veach dynamics. So there is something that happens with the vertical length of my bands as well. So I had this data for the suspension. And I have to preserve it. And this is my S of D. And then I can fix S gamma of D as the similar thing, but this delta should be replaced by delta gamma. It will correspond to one particular arrow. And I can also do a similar thing, but put gamma upstairs. In this case, I will consider what happens to my renormalization, to my suspension part, not to the part of length. Gamma will influence only the suspension. So the domain of my V of the map can be seen as a, maybe I should also write this theta gamma to make it more explicit. So the domain of my V of Rose-Veach dynamics is a disjoint union of S gamma, and the image is a disjoint union of this S gamma. And so V acts on S gamma and take us to the S gamma upstairs. And it's a map onto, because what it does, we take this triple and we go to P prime. It's what we get with this arrow, a new permutation. Then my length should be multiplied by this matrix, and my vertical length also multiplied by a similar matrix. So what we have is that we get a map that is morally invertible. So this is another reason why people are so obsessed with zipped rectangle models. Because if you look at the Rose induction as it is, it's not invertible. But once you add the suspension, you get a map that is morally invertible, because you just substitute these two components, horizontal and vertical, and you get the info of what's going on in the opposite direction. So it allows us to consider the map as an invertible map. And apparently the Rose diagram is very knowledgeable about the modular spaces and type Muller spaces. And we will see which information is covered there. So here I complete my discussion saying that V is basically invertible. And that's the advantage we got when we started to consider the map, not only in horizontal sense as a pure Rose induction, but also with this suspension part as well. Now my goal is first to investigate what's going on with the type Muller spaces. So as usual, we get canonical length and suspensional data. You remember that the length, it's okay, but we also had a vector for the suspension that for any irreducible permutation would give us a possible suspension. So that's what I take, and I get a translation surface. It's canonical. So at the same time, if we start from this data, lambda and tau, and that live in delta and theta pi, we can apply zip rectangle construction, and we get a translation surface. And this translation surface will be just a deformation of this canonical one. So there will be a kind of canonical embedding of this data into the set of marked Teichmüller space associated with this canonical translation surface. And now if we take an arrow at the Rossi diagram, and we consider two suspensions, that would one associated with pi and another one with pi prime, then what we get will be two canonically isomorphic translation surface. They are homeomorphic. And that the corresponding Teichmüller spaces are also canonically homeomorphic. Marked Teichmüller spaces, of course, because we have ramification indices. Great. So now we can formulate some proposition. I'm not going to prove it formally, but it will summarize all the information we have in this direction. So morally, it means that your journey in the Rossi diagram just corresponds to a different choice of the transversals on the same surface or isomorphic surfaces. So when you apply your Rossi induction, you get some action in the Teichmüller space, but all the members of this Teichmüller space, they should be isomorphic. You should not get something different topologically, right? So that's the plot of what we discuss. We take a combinatorial data for translation surface, and we take a connected component of the Teichmüller space, we have an open subset of C formed by the translation surface structures that can be obtained using zipped rectangle constructions. Then we have the following. So C minus U has a real codimension greater or equal than 2 in C. And there exists a combinatorial data and the homeomorphism such that the corresponding isomorphism of the marked Tex-Miller space with G would satisfy this condition. And if we take some other combinatorial data A prime, P prime, and we have a map from M P prime, sigma P prime, kappa P prime to our M sigma kappa, then G star, the induced isomorphism, will take us to C. I'm not going to prove it formally, but I think morally you understand why it should be true and what it gives us. Why do we care about it? Because what does it give us? It's that if you have a rosy diagram and they are isomorphic and they are spanned by two different permutations, then they should be isomorphic. And if you assume that they coincide, then you can consider the element of the modular group that would be determined by G minus 1 G prime, and it would belong to the image of the group group homomorphism, not isomorphism but homomorphism, from the fundamental group to the modular group. So what we mean morally is that the Rose induction, and in particular Rosy diagram, knows a lot about our topology. And all the information about Teichmüller spaces, it's all zipped inside of the Rosy diagram. So we're going to use it now because we started with Teichmüller space. Now it's time to switch to modular space and to understand what's going on there. Why do we care about all it? Because we want to prove something about the Teichmüller flow. We want to say that the relations between Teichmüller flow and Rosevich induction are the same as relations between geodesic flow and continued fractions. But Teichmüller flow was defined in a modular space. So in order to see what is it, it was a kind of geodesic flow in the modular space. So we need to understand how does this Rose induction related to the modular spaces. What it happens when we apply it. So that's what we are doing now. And we switch to this modular space part. So Rosy diagrams and modular spaces. As usual, we had alphabet, Rosy diagram, and Rosevich induction. We took a permutation, and we associate the triple and we add UP star and CP star as the guys from the previous proposition. So we can consider the stabilizer of C. The stabilizer in the sense that the modular group acts on Q. It's a subgroup of it's image of our fundamental group. And so we can consider the following part. So we are trying to look at the Rose induction to the past. So that's why there is plus here. It's kind of, you made Rose induction, you normalized, and now you look to the past. And now you consider the disjoint union over the elements of R of this delta 0 pi multiplied by theta pi, and make smart identifications on the boundary of this set. So what's the goal? What do we want to do? We want to take our zipped rectangle model and to explain, you remember we had to use to glue the surface. So now I want to adapt it to the action of the modular group inside of the modular space, in a way to be able to project what happened in the Teichmüller space to the modular space. So I will make some, we'll take these people and we'll make some identification. So I take lower boundary. It's this one, this part. And I will divide it into two parts. The top half, when the sum of my thetas is positive, and the bottom half when it's negative. And in a similar way, I introduce my upper boundary. It will be the one given by this one. So and as usual, I have top half. In this case, it will correspond to the situation when we make top choice of the winner and loser, and bottom half when we have the opposite choice. So for each arrow, if we have an arrow from pi to pi prime, it will be my arrow gamma. So for each arrow of top tau, we identify the top half of the upper boundary of this guy with the top half of the lower boundary of that guy. And so how do we do that? We take lambda and tau, and we say that we have to multiply them by the matrix by gamma minus 1. And then I do the similar way with, so we identify these people with these people, and these people with these people. And then I have M of D. It's what I get through these identifications. And I can consider nu. It's a union of gamma P star D, G gamma minus 1, EP delta naught pi, theta pi. So pi, it's an endpoint of a path gamma. And what we claim, that once again, I'm not going to prove it or you will be too bored. It's too technical. But my statement is there is a unique continuous map that takes this nu to M of D from here to here. And it's done in a way that P G gamma minus 1 composition A of pi, it's a canonical map. to MD. So this MD, this modular space, we will be, it's a modular space. So it can be identified with a subset of marked modular spaces whose complement has codimension 1. So the canonical volume of this guy is a standard Lebesgue measure restricted to each person, like that. And then we get also, since we have it as a model of the modular spaces, so we can think about modular spaces, we can model them with this simplex that we really can touch. You understand? It was something very abstract, you know, modular space, some pairs of surface plus foliation. And now it becomes something that you really can touch, that you can imagine. And so now it also gives you a natural transversal section for the Teichmüller flow. How does it work? So when you take this lambda tau and you take it to Et lambda, E minus t tau, it exactly corresponds to the fact that you associate lower bound with the upper bound. So it's a transversal section. For the Teichmüller flow. So we want to compute the volumes of these modular spaces. In particular, since we want to prove ergodicity, at some point we will need to apply Poincaré recurrence theorem. But in Poincaré recurrence theorem, you remember we needed invariant measure, but we also needed that the whole measure is finite. So we will need to check that the whole measure of this modular spaces is something that is finite. So first we will normalize the area. And then we will consider the subset of our modular space restricted by the fact that the total area is 1. So S of D that I don't remember where it was, maybe I erased already, but we already introduced it somewhere. So this S of D can be now identified with a transverse section for the Teichmüller flow. So then you can see that if you consider the first return of the Teichmüller flow to this S of D, it will give you exactly the Rosevich dynamics. So return map to S of D is exactly Rosevich dynamics. And you can even see what the return time is. What is it? And return time is given by log lambda 1 lambda b gamma minus 1 1. Here it's a L1 norm. So let me explain you what does it mean. I erased, unfortunately, my picture with interexchange, but basically, yes, I erased it, but basically it means that if you take this model picture we had, and you do a Ross induction, So you have to cut this part. This is the return time is exactly how much you ate in this procedure. It's the proportion of a piece that you ate. Just, you remember what we did? We said that the Teichmüller flow has A and power T, so we need to take log to compute the return time. But morally, the size of the piece that you ate is exactly responsible for the return time. So now what Zoric did, what we discussed at the very beginning of this boring part, he suggested to consider a smaller transversal section. So instead of taking the whole S of D, he took a S star of D. That can be seen as in the following way. So if you take gamma, which is a top type, let's say gamma top type arrow, so you consider the set of S gamma of D such that the sum of tau is strictly positive. So once again, it means that you take all the people for whom the winner is the same. You consider it as a one step. And so your S star of D is a union over all gamma such that this S star gamma of D is defined. So you consider union over all gamma and D, and then you can see that the return time of the Teichmüller flow to this smaller person will be exactly the acceleration of the Razivich induction. And one will need to iterate our procedure as long as the type of the corresponding arrow does not change, or if you want, the winner does not change. Because you understand, if you won once, why it's the same thing, that winner does not change as the type does not change. The type depends who wins, the top guy or the bottom guy. But if you keep the top guy winning, then it means that you do not change the type of the arrows as well. And in order to lose, you need to change the type of the arrow also. So you understand what we did. We proved that Teichmüller flow has Razivich induction as a first return map to a nice section. We found this section quite explicitly. And then we considered a shorter section, which corresponds to a shorter subinterval because you accelerate, so you make several steps in a row. We took a shorter subinterval, and we associated a smaller section, and this Teichmüller flow has it as a first return map, this map. So I want to make you an example to make all this construction relatively explicit to you in the case when we live with torus, and then we will make a break after that, okay? So example. S of D is lambda A positive. We have only two intervals, okay? So we don't have much information. This thing is possible. Tau is positive, tau B is negative. We add the renormalization. It's 1, and we also add another renormalization that the area is 1. This is our S of D. So we can distinguish ST. It's those in S of D whose lambda A is greater than lambda b, so we have a top type. Then SB, they are the same guys, but lambda A is smaller than lambda B. Then we can move T and B to the top, saying that ST, they are the same people, but tau A plus tau B is negative. Sorry, negative for top. Then SB, tau A plus tau B, they're positive. Now we are going to Zorich part, so we have to do this star. They will be still quadrupoles from S of D, such that lambda A is greater than lambda B. Tau A plus tau B is strictly positive. And in a similar way, you consider a bottom part. It's the same, but lambda A is smaller than lambda B, and the sum of two tau is, sorry, here it should be negative, and here it should be positive. And so if you consider people from this part, you write how V looks like. And V is simply lambda A, lambda B minus 1, 1 minus lambda A, lambda B minus 1, lambda B TA, lambda B TB minus TA. And now for V star, it's the first return map on this C star. And you do a similar thing, but you write here lambda A, lambda minus 1, 1 minus lambda A, lambda minus 1. I will write who is lambda in a second. TA, lambda, TB, minus NTA. And lambda is lambda B minus N minus 1 lambda A, where lambda B is assumed to be between N lambda A and N plus 1 lambda A. So you subtract it as many times as possible. And then you know that after that they change their roles. Tau are those who are responsible for suspension. The position of zeros in this zip rectangle model. Is it clear what we did and why it is like that? So, but at least you can use it then to verify my construction in this baby example, if you try to do it by yourself. So you go back to your Rosevich induction, to the zipped rectangle construction. You see how do we divide it to glue it, and you see what Zorich did. So we have to consider lambda B minus N minus 1 lambda A. This is our acceleration, because instead of subtracting every time, you subtract immediately as much as you can. Okay, I think we have to make a short break now, and then we will continue to estimate volumes and to apply it for the proof of unique ergodicity. So I apologize, maybe it was not very well heard. So we start with an example when d is equal to 2, and we try to estimate the volume. And as I said, we just need to integrate. So first we integrate over this part of the boundary. Lambda b ta minus lambda a tb is equal to 1. And this integration gives us lambda 1 minus 1, lambda b minus 1. Now we integrate over ta plus tb, positive tb, negative, lambda b ta minus lambda a tb. So it's always tau, not t. So this gives us lambda a plus lambda b minus 1, lambda b minus 1, but this guy is 1. So it's just lambda b minus 1. So if we try to compute the measure of S of d, we will have the integral from 0 to 1/2 d lambda, lambda 1 minus lambda. So you see that at 0 we have a pole, and this integral is divergent. This guy is divergent integral. So that's why we did not like to treat this one as a main return set. So that's why we had to use Zorych acceleration. And if we do the Zorych acceleration, so this is a measure of S of d. So now we do a similar thing, but for S star. And there we get rid from this lambda. So we have from 1/2 d lambda over 1 minus lambda, and this is exactly log 2. So the measure of, if we try to compute the measure of mu1 of d, the return time is given by minus log 1 minus lambda, and we have 0 at 0, and it cancels the pole. So if you try to compute the integral, it gives you from 0 to 1/2 the lambda 1 minus lambda, but it's not the mu, you need to multiply it to the return time, so it's log, and then the 0 here will react with log here, and so you have a convergent integral, and it's p squared over 12. And the measure that you are interested in, it's twice this, because you have symmetric part. So you need to multiply it by 2. Is it clear what we did, more or less? So we just used this explicit description of the sets we have and computed the corresponding measures. And here you very explicitly see why do we like Zorych acceleration. Because without it, we were in a situation when the corresponding integral was divergent. This is what happens when you have fixed points. So it's your way to ignore fixed points, where Jacobian is 1. Once you accelerate the algorithm, you don't have it anymore. You have a smaller division of the original parameter space. You make a smaller partition, but in each cell, your Jacobian doesn't have fixed points, and so you can compute the corresponding measures. Now, what is the same and what is different in a general case? One needs to be quite patient because it will require a lot of technical work. And the idea will always be as here, but we will need to calculate more and to prove some both combinatorial and analytical statements. So we would like to perform the integration over tau variables, as before. And these variables, they run over the convex cone, theta pi, but they are restricted by the area condition. So as before, we have winner, loser, and they both live at the very end. And then we have the vertical length of the bands in a zip rectangle construction. So H alpha t plus H alpha b is H alpha. And I will also introduce one more guy, couple of guys actually. It's a complement to this H that we already defined. So the sum of these complement people is still the same. And the sum of ht alpha t plus hb alpha b sum of the two should be 0. Let's check whom exactly. B. Yeah, the difference of these two guys with these two is that we remove those who are equal. You understand? So we take this and we sum up over those where inequality is not strict and there it is strict. So we remove the situation when they coincide, when they are exactly those who are the very last one who will participate in Rosevich induction. So now we will consider the top half of our parameter space. So we have lambda, the length. And for all numbers that are not involved in the Rosevich induction, their lengths are preserved. So they are just equal, but for the guy who is participating in Rosevich induction, we have a precise formula that we need to subtract the loser from the winner. And in a similar way, we know what to do with the vertical length of the corresponding bands. We know that if we are not involved in the induction, we are preserved. And if we are involved, here we need to change the length of the loser, and it increases. It is calculated as a sum of the previous lengths, right? That's what we discussed previous times, you remember, when we agreed that we need to glue up two bands to imitate the path. So this is our area. That is the sum of areas of rectangles that are involved in zipped rectangles. So we need to multiply their horizontal and vertical length. And the similar thing happens when we apply Rose induction. It does not change. So it's an equality. And now we will decompose after our theta pi into a finite family of simplicial disjoint cones. So let's take gamma to be a cone on this family. So we can choose a basis. It's a simplicial cone, so it should be presented as a linear combination of vectors of some basis. The basis will be of volume 1. So now we recall that we know how to compute H in terms of tau. And we can rewrite the area condition slightly differently using this description of the cone. I did this because I needed to integrate over tau. That's what we discussed here. But the area looks nicer in terms of H and not in terms of tau. Tau, you remember who they are, right? So H, they are vertical length, and tau, they are responsible for the shift of the intervals. So once we integrate over my gamma, we see that we deal with the following things, that we have to consider some renormalization coefficient on the product of lambda alpha h alpha minus 1. So in order to get the measure of this S of D, what we had here, we need to integrate this quantity, this one, over the top half of delta P, normalized by the condition that the sum of the intervals is equal to 1. Then we need to sum up over all gammas. Then we need to sum up over all permutations. And then we need to add symmetric contribution of the bottom halves, right? So we consider the decomposition into cones, computed for each cone, then sum up. Then we sum up over all the permutations, because each cone is given for a fixed permutation. And then we remember that there was actually also a bottom half, so we will need to multiply by 2. So the really question about finiteness, because what I want now is not to get the final result, the values like in this elementary case, but just to prove that it's necessarily finite. In reality, it's all over this first integration, because then the amount of gammas is limited, and if you sum up over all the permutation, it's also something limited. I mean, it's bounded because you have a finite number of vertices in your Rossi diagram, finite number of permutation of the fixed end. So even if you need to multiply by 2, it will not spoil your strategy. So in reality, we need to be sure that when we integrate this kind of person, we will not get some divergent integral as it happened here. And that will be our goal. We have to check it. And there will be a few technical steps on our way. I will just mention them. I'm not going to prove it very accurately. So to deal with this problem, we will introduce for any proper set B. So we consider the alphabet and we consider a proper set B of it. So we consider a subset EB, the subset of Ri, that will be generated by the tau. In the closure B, such that my H for all A, alpha and B. So lemma 1 that I'm not going to prove, I leave it without proof, but it's simply a combinatorial fact that has nothing in common with interval exchange transformations, is that codimension of EB is greater or equal than the cardinality of B, and moreover, it's strictly greater if the loser is from B. And now, if we have this lemma, we take S star D. It's this cross sections that we get for Zorich acceleration. And in this case, we replace theta pi by theta top pi, where we consider only those thetas whose sum is strictly positive. That's the definition of Zorich acceleration. And it's the definition when we live in a top half. But I want to do everything for top half and then by symmetry apply it in the bottom half. And in this case, I prove the following lemma. Lemma 2. There are two combinatorial facts and one analytical. So for combinatorial one is that codimension E star B, it's what we have instead of E of B when we live in this part. So this codimension is strictly greater than the cardinality of B for all proper B, proper subsets. So this person, once again, it's what? We consider those tau such that H alpha is 0 for all alpha from B. Okay. And now in order to complete the proof, we need still to add one more analytic ingredient. Combinatorials are on place. So what analytical one does? I consider delta 1 as a set of a length. They are positive and their sum is 1. And then I consider B as there. It's a subset of A. And I consider a piece of delta 1 as those for whom there is a 0 component for everybody who is not in our subset. So we only consider vectors whose non-zero components belong to this B. And I consider linear forms L1, LP, M1, MQ. They are linear forms that are positive. On delta 1, and I will consider the following ratio. Have L1, LP, M1, MQ. And let me introduce the following numbers. M plus of B it's the number of indices such that LE of lambda is equal to 0 for all lambda who live in delta 1 of B. In a similar way, I define M minus. So it will be everything like what we did, but L should be replaced by M. And then M of B is their difference. M plus of B minus M minus of B. Now we state a lemma that will connect combinatorial conditions from first two lemmas with our main goal, namely with our idea that we can prove integrability. So we say the following thing. Assume that D plus M of B is greater than cardinality of B, holds for all proper sets. Then R, which is a ratio of these guys, is integrable on delta 1. The converse is also true, but we will not use it, so I will not pay attention. This is lemma 3. Lemma 3 I'm going to prove, but before I prove, I will show you how to apply it and how to complete the proof of our main statement. Otherwise, I think it will be hard for you to motivate yourself to learn something about lemma 3. So let's check the finiteness of measures on M1D and the star D using these three lemmas. So the total masses of these measures, as we already discussed, it's a finite sums of certain integrals over top and bottom halves of this delta 1, right? So let's consider the case of top halves. Then for bottom, we will multiply by 2. It's not a big deal. So top half means that lambda hat is strictly positive. So we will consider lemma 3. We have lambda hat variables, and their sum is not equal to 1. But we know that the sum of the original lambdas is. So at least we can be sure that we could not increase them all twice, so this should be. You understand the connection between the guys with hat and guys without. It's all the new coordinates. So what you do after one step, you had to, at most, you add them all to one person, right? And it only happens if this person was big enough, so exceeded their sum, but still was smaller than sum of all of them plus one more. So it cannot be that you increased it more than twice. So you cannot say that it's equal to 1, but you still can bound it at least by 2. Now, let's start with M1. So we look at the return time of the Teichmüller's law to SD. You know what is it? We discussed that the return time is given by the length of this interval that you cut. You have to consider log of this thing. So it will be a log of sum of these guys. Or if you want, it's minus log 1 minus lambda alpha b. You have to consider those who were not subtracted, so that's what we get. So we will integrate it, and you can integrate it literally, almost. You have this time, you have renormalization constant, and you have this thing that we discussed before we talked about lemmas. I think it's somewhere there. This lambda AHA with heads. So you have to do this. So you need to integrate it over the top half of lambda. And we recall that our h is nothing else but the result of application of our antisymmetric form to the shifts. So we apply the previous lemma to this function. We take p equal to 1 and q equal to d. So our ratio will be just L1 on M1, etc., MD. And our L in the previous lemma will be lambda alpha b, the guy we cut. And he coincides in its length all the new one because it's a loser. And in the denominator, you take this that is hard to analyze for you. So you put them to the denominator. So you need to check that the conditions of this lemma are satisfied. And if we are lucky enough with all these functions, right? So you take this as Lm, and you try to apply lemma 3. If you are lucky enough and conditions of lemma 3 are satisfied, then the ratio will be integrable. So your integrable means that if you integrate over a finite set, you will get a finite measure. So it's enough. You only need to be sure that this condition holds indeed for all these proper sets and so on. So we take a proper set. And we do a similar thing. We need to compute M plus. But what is M plus? Let's look here. You remember we computed the number of indices such that this condition was satisfied. But there are not so many indices now because we have only one form. We have only one L. There we had P L's, but P is equal to 1 in our case. So M plus is something rather elementary. We have only one choice, that either it's 0 if our loser lives in beta. Either it's 1 if it doesn't live in beta, right? Do you agree? It's something we can analyze. So in this case, what can we say? That if we look at the sum of lambda A, H, A, I, because we need also to check, we need also to check what happens with Mi here, and then to compute M. And so if we look at this person and try to analyze when it is 0, for all lambda in delta B1, it can only happen if H is 0. But this only happens when our tau I belongs to EB. So here is the moment when we can apply our combinatorial lemmas. So by these lemmas, we know that our Mi does not increase D minus cardinality of B. So we can see that the conditions are satisfied, we are happy. So we use these lemmas to check that, lemma 1 we used to check that in case of M1, the conditions are satisfied, the conditions of lemma 3. And lemma 3 gives us the result. Is it clear? Now we do a similar thing for this S star, because in this case we have to forget about this log and to see just the product of sigma alpha, lambda alpha, hat, h alpha, hat I, minus 1. So we integrate over a top half. P is 0, Q is equal to D. We don't have any P, so it's stupid to compute M plus. We only need to look at M minus, but we know everything about M minus. We already saw this set, so we know what to do, and we are happy to apply our lemma 2 to be sure that all the conditions of lemma 3 are satisfied, and we get the result. So we are able to prove that these volumes are finite. It's not an easy task to compute these volumes, however. For example, there are many specialists in computing volumes of modular spaces in our lab of cluster geometry. They use some very advanced techniques of topological recursions and so on. Better to attend the seminar on Thursday to know more. But in any case, with this technique, you cannot compute anything in high genus. It works well for genus 2, as you saw. You may try for genus 3, but in high genus, this will not lead to you to the success. There is a formula how to compute the volumes of modular spaces, and it's due to Alex Eskin and Andrea Kunkov. But morally, it's very different from what we did here. However, for us, it's enough. We get enough information. We can write a measure estimation. And so we are ready to apply it to prove unique ergodicity. So let me do that. If we have enough strength and time, I will prove you lemma 3. If we don't, I will leave it in my notes. You can recover it from there. In any case, it's something technical and not very ideological. So unique ergodicity statement. First, I mentioned already that we want to apply this contraction argument, but we need a metric, and the metric that fits well for it is a Hilbert metric. So I recall you, what is it? You take an open set in a projective space. It's the image of an open convex cone. In R n plus 1. And this closure should intersect some hyperplane only at the origin. So we take BC, it's a log x minus a, y minus b, x minus b, y minus a. It recalls you a little bit probably the formula we used to write when we were studying hyperbolic geometry. And what is important to know about Hilbert metric is the following property, that if you had a projective isomorphism, sorry, phi of C, closure, then C, so there exists K in 0, 1, such that for any x, y in C prime, the distance between phi of x, phi of y is smaller or equal than k dc xy. In particular, what this condition means, you see, it means that if you have a contraction, which is a strict contraction, you can be sure that Hilbert metric, Hilbert distance decreases when you apply it, strictly decreases. So now we are happy, we can apply it to get the unique ergodicity statement. So we will not care about those who are non-minimal, because in any case they all live in a subset of codimension 1, thanks to kin. So we will assume that we are only in a Kin's space, because they will not influence our condition. And as you already understood, it's enough to prove that this person is a ray. So then we can apply a Poincaré recurrence theorem to the Teichmüller flow. And that's why we fought so much to get this statement on the finiteness of the measure, because Poincaré recurrence theorem requires that we live in a finite measure. Otherwise, we cannot use this Dirichlet principle that was the base of the proof of this theorem, right? So we are allowed to use it, and we apply it to the Teichmüller flow. And that's what we get, is that we can be sure that for whatever length vector lambda, there exists an initial segment gamma s of gamma t, which occurs infinitely many times in gamma t, and such that all coefficients of the matrix B gamma S are positive. So gamma T is gamma S, gamma 1, gamma S, gamma 2, and this gamma S, maybe you had this here gamma 0, it doesn't matter. So this gamma S appears on the piers. And then, if you have this, you can apply this gamma S is the one from Marmi-Moussaieff theorem, from which I started my lecture today. So this is the guy for whom the matrix is necessarily strictly positive. All the coefficients are strictly positive. So to this matrix, you can apply this observation. And other maps, they will be not necessarily strictly contracting, but they cannot be expanding, right? Because they are matrices whose coefficients are 0 and positive numbers. So you combine strictly contractive and non-expanding matrices and maps, and as a combination, you will have strictly contracting map. And so you will have just a ray here. So to put it short, why did I need this statement about finite volume? I needed it to be sure that I have this gamma S appearing infinitely often. that I will be back to this piece of the rosy path infinitely often, and it will appear everywhere. There will be maybe some pieces where we don't have such a property, but again and again we will be back to this part. So that's basically the idea. You find a piece where you have necessarily strictly positive coefficients. You check that you go there regularly because of Poincaré recurrence theorem, and then you check that others do not spoil much, and you consider the whole thing and get the final result. Here we are. We are done with the proof of unique ergodicity. And next 2 lectures will be taken by Sergei Konstantinovich, who will tell you more things about modular spaces, and results by Maria Marzakani on the geometry of modular spaces. And then I will complete the proof of ergodicity of Teichmüller flow, and will just tell you what else people do know about the dynamics and geometry of interval exchange transformations. I think we can stop here, and you check in my notes the proof of lemma 3, because it's technical and not so exciting. Thank you very much for your attention.